Okay, so let's start. Very Morrison from Survivor. I'm going to talk about some old tricks. No.
New tricks? A good old fashioned. So thanks very much. It's a pleasure to be here and to talk at this conference. So I'm going to talk about SL2Z, and I'm going to tell you some old things and some new things, mostly old things, of course. SL2Z has been around a long time. So the sort of first point about SL2Z, as we all know, is that SL2Z shows up in interesting ways in moduli elliptic curves. And the way that a complex analytic geometer, or actually a complex analyst, would present this would be by use of the Weierstrass P function. So the Weierstrass P function is a doubly periodic meromorphic function on the complex plane. It descends to a meromorphic function on C modulo the lattice generated by the two periods, 1 and tau, and I'll take tau to be in the upper half plane, so that I get a decent lattice there. And then the Weierstrass P function has an explicit expression, which is really simple to write down. This is 1 over z squared plus the sum over non-zero pairs of integers of 1 over z minus mn minus tau squared. But to get it to converge, you have to subtract 1 over mn plus tau squared from those terms. And then you get a meromorphic function with a single double pole at each lattice point, and this sum is absolutely convergent on compact subsets on the complement of the lattice.
You said you would keep that size.
I'm sorry?
You said you would keep that
No, I said I would keep the size that was before it was
Yeah, it was bigger than that.
It's bigger than All right. There's only 3 lines per board. Okay.
That's right.
Okay. So, what Weierstrass showed, if you are sort of clever and take the derivative of this guy with respect to z, you end up with something that starts minus 1 over z cubed. And what Weierstrass shows is that there's an algebraic relation between these two quantities whose coefficients involve Eisenstein series. So I can define the Eisenstein series E2k of tau to be 1 over 2 zeta sk times the sum, again, mn not equal to 0, 0, to z2 of 1 over mn plus tau squared. The normalization is because some people want to define their Eisenstein series using relatively prime pairs of integers instead of full ones. Yes?
Doesn't it mean m plus n tau squared?
I certainly do. Funny how I just kept writing and saying the wrong thing. Okay, good. Yeah. Huh? There is a K which was missing. That's correct. So, 1 over m plus n tau to the 2k. Thank you. You could see well enough to know there was no K there. So I was doing my job. Right. So by taking y and x to be slightly normalized, I multiply by some constant to get a better normalization for my equation. I end up with an equation of the form y squared equals x cubed minus a third e4 of tau x minus 227 e6 of tau, which is not the conventional normalization in the literature, and here x was 1 over pi squared times the Weierstrass function to keep everything well defined, and y was 1 over 2 pi cubed times the derivative. Okay, so the moral of the story is that if you're given an elliptic curve from a complex analytic perspective, you end up getting an embedding of it, so this could be projectionized, you end up getting an embedding of it into complex projective space. And conversely, using Wicker-Bobble and Jacobi, how can be recovered as an integral over gamma 2 of dx over the square root of x cubed minus a third e4x minus 227 c6 divided by the same integral over cycle gamma 1. And in the denominator, I'm going to make my life simpler by setting f to be minus a third e4 tau, and d to be minus 227 c6 of tau. And of course, what I mean is that I have to take appropriate basis for the homology of the elliptic curve, and the standard way to do that is to look at the three roots of the cubic equation x cubed plus fx plus d, make branch cuts in the complex plane, and do my integrals around explicitly defined contours, gamma 1 and gamma 2, where gamma 2 crosses into the other two, and therefore only meets gamma 1 in one point. And then this orientation defines process. So this is a theorem, this is a 19th century theorem, that you recover the same tau if you do the elliptic integral, the ratio of elliptic integrals, or you can start with the tau and get the corresponding equation. So how do we do this in algebraic geometry? Well, it's pretty well known that if you start with an elliptic curve, then over an arbitrary field, but I'm going to pick the ground field that has characteristic not equal to 2 or 3, then you end up with an equation of the form, so elliptic curve means G is 1 with a point, so I've got to have a point over my field, and I end up with an equation of this form, initially. Sorry, I did say characteristic 2, it was 2 or 3, so let me not even bother with that mental form, and I'll just write it as x cubed plus fx plus g. Zariski locally, and there's an ambiguity, so the ambiguity in this form, you can look this up thank you. There's an ambiguity in this form, which you can look up in the Leeds formula, and the ambiguity is that x and y, f and g, should go like x goes u squared, y goes u cubed, f goes u to the fourth, and g goes u to the sixth, for u in units. So these days we understand that, we've understood for a long time in algebraic geometry that this problem of elliptic curve does not have a fine moduli space. It has a depth of course moduli space. The J line, which is the upper half plane mod this SL2Z quotient, the SL2Z action. Sorry, I forgot to mention that how SL2Z acts on here, but if you change basis from one basis of first homology to another, you end up acting on the ratio by a linear fractional transformation. Tau goes to a tau plus d over c tau plus d. And there's no fine moduli space, so but these days we understand that there is a moduli stack. In fact, this was the problem where this together with the Lee-Mumford curve between C were the problems where people really started to understand what stacks were supposed to be. Here you can describe it very explicitly. There are all of these interesting covers which are fine moduli spaces for elliptic curves and level structures. And there's a whole lattice of these covers, of these congruent subgroups of SL2Z, and if you line out by the various congruent subgroups of SL2Z, you get a whole lattice of covers of the original space, And that defines the structure, as we now understand, of a stack on that space. There is an alternative way to talk about this stack, which is to use the Weierstrass equation, the one with the f and the g. By the way, my convention for the f and the g is not quite the same as number theory is. To use the Weierstrass equation, so I should think of the fact is that x cubed plus fx plus c has distinct roots if and only if the quantity 4f cubed plus 27g squared is not equal to 0. So if I'm really trying to do elliptic curves, a non-singular elliptic curve, this is the condition that I need, and I can describe the stack by looking at the localization of an A2 whose coordinates are f and g at 4f cubed plus 27g squared, and take the stack quotient by Gn, where what I want to do is give weights 4 and 6 to f and g in the Gn action on Apophis space. So this is the sort of modern way of describing the moduli of elliptic curves. So I want to give a topologist perspective on such a moduli space. I'm not a topologist, but I think I know what their perspective is. So what the topologist is going to say when confronted with a construction like that? Well, first of all, this description in terms of f and g was modulo the GM action was Zariski local, and what that means in a global context, as we also understand well in algebraic geometry, is that we need a line bundle over our base. So if we have a non-affine base and we're trying to describe a family of elliptic curves over it, we need to understand what line bundle we're using to do that construction. And a topologist, thinking about the data of a line bundle, thinks about a universal C bundle, and the confine space for those guys is CT infinity. And there's a nice universal bundle. So this is a universal C bundle over CT infinity. And now I'm just going to follow that description. So I want to take a space, which I'm going to call M, and that will be the set of pairs f and g, which are in the sections of the fourth power of the universal bundle, plus the sections of the sixth power of the universal bundle, with the property that 4f cubed plus 27g squared is not equal to 0. Sorry, I have to subtract stuff. So this minus the locus, where 4f cubed plus 27g squared equals 0. So that's a nice space, which still maps out to CT infinity. And here's the proposition, which is the new thing about SL2Z. It's very hard for me to believe this is really new. I've talked to a bunch of topologists about it. Everybody says, yeah, that sort of looks okay, but it's kind of like this other thing, which is a different stack, which I'll mention in a second. And I have not been able to find this in the literature. So I may need a person doing this proposition is new, but once you see it, it will be really apparent that somebody could have noticed it before. And that is a calculation of the fundamental group of this space. So this is the same space. I am using, if I was doing complex geometry, I could sort of interpret the topological meaning of the modular construction just by map to this space here, this map of the homotopy of this space here. And so if I'm interested in knowing things like, in the classical case, the fundamental group that I would see by taking the complement of the discriminant locus in an elliptic vibration, I'd be interested in this. And the answer is SL2Z.
So, when you say you subtract 4f cubed plus 27 equals 0, you mean that identical is 0 or that has a 0 or?
Identically 0. This is not a case by one. In fact, it's not a case by one. Sorry, I don't know if it's a case by one. I haven't actually thought about what the higher homotopy would do. So let me tell you the related topological fact, and that is, if I instead ask for, and now I'm going to use C2 because it's really about the complex number, if I instead ask for the fundamental group of C2 minus, and again with coordinates F and G, minus the set 4S cubed plus 27G squared is 0, then that is the breakthrough on two vendors.
What's the map which is infinity?
You know, I said this was sections, but what I really meant was fibers. I guess what I really meant is this. Points and fibers, yeah. That's what I really meant.
It is a direct sum.
It is a direct sum, thank you. Doesn't have gamma, that's a direct sum. That's right. So that removes the ambiguity of it. Yeah, thank you. So that's a braid group C3. And the center of the braid group is the integer. And if you take the braid group modulo the center, you end up with TSL2Z. So this is something that all methodologists do know. But what was not so obvious to them, that doesn't seem to be in the literature, is that when you do this construction, which is the natural and prolific curve, you actually end up with SL2Z. So, by the way, although I didn't really point it out, when I was taking the quotient by the upper half plane, the center of SL2Z, which is just minus the identity, acts trivially on tau. And you might have thought that you were just supposed to be using SL2Z to begin with, but as those of us who study the generations of elliptic curves know, that extra -1 is important. It's important because it's a universal automorphism for all the elliptic curves. It's actually one of the reasons that there isn't a good moduli space for elliptic curves. And I could have done the same thing with weights 2 and 3 instead of 4 and 6, and still had that would still preserve this action. So if I had done pi1 of the moduli space tilde with weights 2 and 3, I would have gotten the PSL2Z. So what is that the moduli of? Well, is it on or is it still here? The reason for the necessity of the 4 and the 6 power is that I have a y in this equation. So if I were only looking for cubics with distinct roots instead of elliptic curves, then I could actually mod out by slightly different scaling, where I would use the second and third power of u squared. That would be enough for the scaling. Then I would get PSL2Z, and that is something that you would expect. And this discussion here, the PSL2Z, turns out to exactly geometrically be the same thing, because the braid group is thought of as in this case, this space, is thought of as the configuration space of 3 points in the plane, and the unordered points in the plane. And so that maps clearly to PSL2Z action, but then with the braiding you have some more complicated things going on. So you end up with exactly getting the remaining central element being the -1 in SL2Z in this case. So, as I sort of suggested, what I'm interested in is general situations of, say, a flat family of algebraic varieties X to B, flat with fibers of geometric genus 1, And in such a context, I'll have a discriminant locus, which is the singular fiber. Images of singular fibers with singular fibers. And over that discriminant locus, I'll have, x minus pi over delta, mapping to v minus delta. It'll be one of these families of elliptic curves. And what we've just seen is that there's a topological mapping to this modular space n, and therefore a map from the fundamental group of the complement into the fundamental group of the modular space n, which we've just decided was SL2Z. Now, from another perspective that's not too surprising, we've got the possibility of taking, let me use pi again for the restriction, let me use pi 0 for the restriction. We've got the possibility of taking R1 pi 0 lower star of Z. So this is a Z2 local system of fiber Z2 on V minus delta. And again, complex analytically, you would expect it to be described by a representation of the fundamental group on SL2Z, GL2Z actually. But if you look more carefully, you discover that it does preserve the determinant. So it actually goes into SL2Z. Maybe I use a smidgen of posture there. And this is the same representation that we just described from the topological perspective. But what it means is that we can draw conclusions about certain parts of the behavior of limiting families just by considering the SL2Z action itself. So let me mention the application in the background. So for nearly 20 years, physicists have been studying something called F-theory. And what F-theory does is it uses an SL2Z symmetry of one of the string theories, so-called I2B strings, to generate interesting physical models. So what does it mean that there's an SL2Z symmetry, and that's the way you want to use it? It means that you want to write down physical quantities in the theory which are invariant over the SL2Z action. And in fact, things that are covariant in the way the modular forms are covariant will be good if you can match covariant things together to end up with physical observables. So it doesn't mean that everything is a function of the J invariant, but that you should use the SL2Z symmetry in a very nice way. And the typical method has been to use a flat family as above. So we end up with a use of elliptically fibered algebraic varieties to produce interesting models in physics. The point of this new observation is that a lot of the detailed information about the geometry of that flat family is actually contained in the SL2Z information alone. And in fact, we can use F, G, and the GM action alone. Really, that should be using a U1 action. From the topological point of view, the GMC action is topologically doing the same thing as the U1 action. So I can use FG and the U1 action alone. And things that we have learned by studying, for example, the ways in which fibers can degenerate in families of elliptic curves for this application, many of those things can actually be rewritten just as properties of SL2Z and the way that it acts on these spaces. So let me mention an easy restriction that one gets from Haas theory. So if B, say, is a closed disk, if T is a closed disk, and this pi is some, maybe now I'm in the complex analytic category, pi is some nice elliptic vibration over the disk, and I look at the, and B intersected with delta is the origin, and I choose the holomorphic generator of pi 1 of B. In other words, the orientation of the complex number is determined as the generator for pi 1 of B. Then I end up with a conjugacy class in SL2Z associated to the generation. And there's a restriction on those conjugacy classes because I've got a degenerating family of Hopf structures. So the monodromy theorem in Hopf theory implies that this monodromy matrix, which I'm going to call M, is quasi-unipotent, and that quasi-unipotent classes in SL2Z are none. So here they are. So there are parabolic elements which look like 1n, 0, 1, or -1, -n, 0, -1. And then there are a bunch of elliptic elements. There's the center of the element of order 2. There's an element of order 3 which are labeled 4 and 4 star. There's an element of order 4 which are labeled 3 and 3 star. And there's an element of order 6 which are labeled 2 and 2 star. What I've written is not the full set of such elements, but only a representative for the conjugacy class. There are lots and lots of such elements. In fact, if you have a parabolic element, there's an associated boundary point at the upper half point. So there's, you classify the upper half point as an ideal boundary consisting of all rational points on the real line together with infinity. And there's a fixed point for the extended group action on that ideal boundary. So there's one of these conjugacy classes for every rational number, up to plus or minus 1. And similarly, you can identify the other points of orders 3, 4, and 6 with specific points in the fundamental domain for, the way I've written it, in the fundamental domain for the action of SL2Z, but of course there are conjugates of this, which are the other, many other copies of the fundamental domain. Infinitely many other copies, so there are lots and lots of classes in this case. So there is one restriction that I do not know how to generate using this very general setup that I'm discussing now, and that restriction is n greater than or equal to 1 in my table. So for parabolic elements, again with the orientation, all the orientation dimensions that I mentioned, only positive n's appear, and for the, well, these are the same parabolic elements multiplied by -1, so again, only positive n's appear. And that's something whose only proof I know uses the full Kadira classification of singular fibers. So I don't know how to do it sort of independently of that, but I will point out that physics provides something called antibranes for the missing solution. However, in those physical descriptions, you lose holomorphicity if you put in antibranes, and indeed, the fact that I can't, in the algebraic geometry or complex analytic geometry context, find the negative values of n is consistent with the physics description in terms of these so-called antibranes, anti-G7 branes. Okay, so I've got the monodromy information, which, by the way, Kadira works fairly hard to get from specific examples, but the monodromy information comes as a sort of distinguishing feature of the complex codimension 1 singular model. There's another distinguishing feature of the complex codimension 1 singular model that I want to describe.